Hi everyone, and thank you for watching this presentation. My name is Colin Dandumont and I'm a PhD student at the University of Liège. Some of you may know me from previous live meeting. Today I will present the work of my team about an interferometric smallsat to study exoplanets. This work is done in the Centre Spatial de Liège in Belgium in collaboration with my two supervisors, Denis Defrem from Leuven and Jérôme Loïc from Liège at Delft. Right now, in less than 30 years, more than 4,500 exoplanets were detected and more than 7,800 exoplanets are still candidates. This number is increasing every day and this is really astonishing. If we look to the detection method, we can see that the transit method is the most prolific one, then the radial velocity one. And as you can see here, direct imaging is still a marginal technique. However, it needs really to be increased. Why? Because direct imaging allows a direct knowledge of the exoplanets and offers us lots of information about the exoplanetary system. Moreover, indirect methods as transit are strongly dependent on the orientation of the exoplanetary system. To do so, Nulling interferometry is considered as one of the most promising solutions to tackle this problem. And really, it offers us the possibility to spectrally characterize rocky exoplanets in the habitable zone of nearby stars. A mid-infrared space-based Nulling interferometer needs therefore to be developed, and that's really the main reason why we are all gathered here for this meeting, to talk about LIFE. LIFE, as you know, seeks to be an L-class mission, a free-flying interferometer around the L2 Earth Sun Lagrange point. If the yield is quite large, as the team is showing us in a submitted article, such a mission is costly with a high risk. That's the main reason why we are here to talk about a Precursor mission, so a smaller mission but still with scientific capabilities. The idea, of course, is not new. In the 2000s, Darwin and TPFI were the largest missions, and numerous concepts as Pegasus for Europe or FKSI and CIDIS for the US were envisaged. So the goal of our Precursor is to validate and demonstrate interferometry in space. To keep things simple, we are considering only pupils on the same spacecraft, so no free flying. We are looking to three main architectures, 2 CubeSats, so a 6 unit long and a 12 units long, so basically 60 centimeter and 1.2 meter of baseline. And why we are considering CubeSats? Because since a few years, we have really an emergence of wonderful astronomical CubeSat mission as PIXSAT, Asteria or Qt. We are also considering a larger platform, so a PROBA-like platform, with this last a 5 meter baseline length. And as you know, increasing the baseline length allows us to directly increase the angular resolution. We can also increase the pupil diameter up to 25 centimeters, which gives us a better sensibility. In our study, we also consider the former FKSI, but the results will not be presented here because this is clearly a M-class mission. The different satellites are all based on a fiber-coupled Bracewell architecture, so with 2 apertures. You can see here a block diagram showing the optical train from the telescopes up to the constructive and destructive output. So you have the 2 telescopes, the transfer optics, followed by the tip tilt and OPD correction stage, then the fiber injection, and in fine, the beam combiner. To analyze the scientific capabilities of our concepts, we developed a radiometric budget. This budget is presented and well explained in a paper published last year. Here on the scheme, you can see the main contributors. So we considered the stellar flux, or more precisely what remains after the null, the planetary flux, which takes into account the reflected and the thermal part, the exozodiacal disk, and the zodiacal flux, and of course the background flux from the instrument. all concepts have different instrumental temperature. So the colder the instrument, the better the sensitivity. But as you may understand, it is really more difficult to cool down a CubeSat than a PROBA-like satellite. Inside the satellite, we also considered the injection stage, and as well all typical interferometric noises. But okay, we have a radiometric budget, but we need to apply to some targets. Therefore, with Jens Kammerer and Sascha Quens, we used their tool, PPOP, so their Monte Carlo simulation tool that generates synthetic planet populations around 326 real main sequence stars in the vicinity of the Earth, so in 20 parsecs from here. In fine, we have 86,000 planets generated, and you can see on the left a planet radius stellar insolation plot showing you the distribution of this planet, which are based on the Kepler statistic. We also applied our radiometric budget to the 28 newest exoplanets, but these results were presented last year in the SPIRE Astro conference. Here we are more focused on the whole catalog. So you can see on these three figures, for each configuration, a radius stellar insolation plot showing you the mean detectability. So the bandwidth is selected to be optimum for each configuration. The central wavelength varies therefore between 0.5 to 2.5 micrometer depending on the platform. No platform stability constraints are considered at this stage, so you need to be cautious with these results. This is really the most optimistic ones. So you can see here the CubeSats, and the results are nice, but not so high. So a few exoplanets. This is still really cool, but you need to look to the PROBA-like satellite to have like more than 100 exoplanets detection in total. We also look to the impact of unwanted optical path difference. So in color, you have the mean detection, and you may see that the requirements are very stringent. 1 nanometer, so just here, is really sufficient to drastically impact the yield for the CubeSat. And with 5 nanometer, the yield is divided by a factor 2 for the PROBA configuration. You can also see here the wavelength dependency. To put this number in perspective, it was estimated that FKSI and Pegas can co-phase the two beams with a precision of around 2 nanometer RMS. We also looked to the tip-tilt angle, so a relative angle between both pupils. The results are also stringent, around 25 milliarcsecond for the CubeSats. After that, we lose too many detection, and around 40 milliarcsecond for PROBA. And once again, we are close to the FKSI and Pegas results, which were about 25 milliarcsecond RMS correction. In complement of this radiometric study, numerous students that I supervised with Jérôme and Denis worked on the subject and wrote their master thesis. An orbit analysis was done 2 years ago, followed by a thermal analysis on this orbit. We also looked to the fiber injection theory and deformable mirror to compensate some wavefront error and the tip tilt. Last year, we looked a little bit more in details to the optical design and the achromatic phase shifter. This last element is really a critical element for the Nulling interferometer. Why? Because with a wide bandwidth, we really need an achromatic pi phase shift. These works are really great, but of course it will take lots of time to present them in details. And so I urge you to contact me or Jérôme or Denis if you want more information, or just search this name on internet and you will find the master thesis. To conclude this presentation, we all agree here to say that Nulling interferometry is one of the most promising solutions to spectrally characterize exoplanets. what we do is to look to the role of Precursor or life, and what would be a possible architecture. So, with the emergence of astronomical CubeSats, we really wanted to look to the capabilities of such satellites. So, with our radiometric budget and a state-of-the-art synthetic planet population tool, we derived the mean detectability, the yield. I also presented the challenge ahead because OPD and typical requirements are really hard, but we mean feasible. And the next steps are clearly to continue in that way, and looked to an end-to-end optical layout, a mechanical and a thermal analysis of the instrument. Jérôme Loïc, my supervisor, is really pushing that way here in Liège with my work, or more recently in Delft. So thank you to listen to this presentation. I really hope that you enjoyed it, you enjoyed this summary, and of course feel free to contact us if you have some questions or remarks. Thank you.